Hello everyone. This video topic is Poisson distribution. It is a widely applied discrete probability distribution. So in this lecture, we'll discuss it in detail. First, we briefly look at the Poisson distribution, that is definition, and I try to derive the PR map of the Poisson distribution. And finally, Poisson distribution is closely related to the binomial distribution. So I will introduce it with your example. Okay. The Poisson distribution is a discrete type probability distribution that expresses the probability of the number of events occurring in a specific interval, like this, such as distance, area, and volume, with a known constant mean parameter. You know, it is called the Greek alphabet lambda. Okay. For example, it is a probability distribution of the number of bird flu in Gangwon-do during a day. Okay. Or when you are interested in the probability of the number of asthma patients in Seoul during 1 year, we can use the Poisson distribution. It is named after French mathematician, that is Simon Dan Poisson. Okay. The probability mass function of Poisson is as follows. Okay. You know, it is a distribution with a positive value, lambda, which is the mean of a fixed interval as a parameter. Okay, and you know, since the outcome of the random variable is the number of events. Okay, so the range has a value from 0 to infinite. Okay, that is 0, 1, 2, and infinite. So now let's derive this PR map. Okay. Before deriving the PR map of a Poisson, we'll look at a few facts. Okay. We'll let a small letter A and B as a constant. Then the first fact is that when the n value has an extremely large, that is going to an infinite, then A over small n converts to 0. For example, you know, A over 10 equal 0.8. A over 1000 equal 0.008. Okay, A over 1000 equal, you know, 0.0008, like this. 1000 A equal 0.00. This value is approximately 0. Okay, so if the numerator is your fixed value and the denominator continues to increase, the value converts to 0. Okay. Number 2 is that when it's sufficiently large, that is n goes infinite, the value of a numerator is n to a power, and their denominator is n to a power plus the constant to b converts to 1. That is plus b, and you multiply the 1 over n to a power to the numerator and denominator, and you can write as the 1 and 1 plus b. Okay. And then as when small n goes infinite, you can see that this term goes 0. So this value converts to 1. Okay. Also, the n factorial divide the n factorial plus p converts to 1 as n goes infinite. Okay. You can also find that n factorial divide n factorial plus p equal 1 over 1 plus n factorial p, and as n goes infinite value, this term equal also 0. Okay. Also, n factorial divided n minus a factorial multiply and to small a power equal 1 as n goes infinite. Okay, the numerator can be expanded using the definition of factorial like this: n multiply n minus multiply 1. So we can write as n to the small n power plus. Okay, and the denominator can also be expanded as follow: n minus a factorial is n minus a multiply a minus 1 multiply this and to small a power equal small n to power n plus. Okay, so this value is equal this value. Okay, therefore you divide the denominator and numerator as a 1 over and the small n to power. Okay, then 1 plus 1 plus So when n has extreme value, then this term goes 0, 0, 0. Okay, so equal 1 over 1 equal 1. Okay. 1. Okay. Finally, 1 minus a over small n to the small n power has a small alphabet e to the minus small a power when n goes infinite. Okay, you know the small alphabet e is called Euler's constant or Napier's constant. Okay. Okay, so in this lecture, I will not prove this fact. Okay, so please just memorize it. Okay, so based on this fact, let's look at the PR map of a Poisson distribution. We assume that there is a specified interval as follow, and the average occurrence event number is a constant lambda in this interval. At this time, the discrete random variable x is defined as the number of events. So the outcome of x has value equals 0, 1, 2, then infinite. Okay, so let's find the probability when x equals k. That is, let's find the probability when the number of events is k. Okay. First, let's split this specified interval into two parts. Okay. Then there each interval, so we let the interval 1, interval 2 has the average occurred event value as lambda over 2. Lambda over 2. Okay, so the probability of x equal k can be seen as your probability when the sum of the number of events in each interval is k. That is, x equal number of event interval 1 plus interval 2. Okay, so for example, when there k equal 5, okay, then the interval 1, the number of interval 1 can have 2, or interval 2 is 3. So the sum of the number of events in this interval equal 5 equal k. Okay, or 1 plus 4, 5 plus 0, and so on. Okay. And case 2 is that divide this interval into 3 parts. 1, 2, 3. Then the average number of occurrence in each interval is lambda over 3. Lambda over 3. over 3, and we letter this interval I1, I2, I3. Okay, so the probability of x equal k equal the probability when the x equal the sum of the number of occurrence in this 3 interval is k. That is number of 1 plus interval 2 plus interval 3. Okay. For example, when equal 5, the number of interval, no, the number of an interval is the 1, interval 2 equal 2, interval 3 equal 2, or 0, 5, 0, or 0, 3, 2, and so on. Okay. Similarly, if this interval is divided into 5 equal parts, E1, E2, E3, E4, E5, and each interval have an average lambda over 5. Right, okay. So this probability is equal k is the probability that the sum of the number of occurrence in this 5 interval is k. 1, 2, 3, 4, 5. In case 5, let's divide this interval into small n part like this. 2, 3, 4. So we can letter interval 1, interval 2, interval 3, interval small n. So you know interval I become very small as the number of split, the n, small n, increase. Okay, and then in each interval, an event occur or not. Also, in the interval 2, an event occur or not. Occur or not. Okay. In this interval also, an event occur or not, because the interval is very small. You know, that is, it can be seen as n times Bernoulli trial. Okay, and you know, and its interval has an average value of lambda over n, lambda over n, lambda over n. Okay, and we can see this as a probability. Okay, that is the success or probability is lambda over small n. Okay, therefore random variable x means the number of events occurring in this fixed interval. So x can be seen as the number success in n times Bernoulli trial. Okay, so a random variable x can consider so we consider the distribution of x as a binomial distribution when the n has sufficiently large, that is n goes infinite. Okay, x follow a binomial with n binary trials, and the probability is the lambda over small n. Then the PMF is as follow. Okay, and choose small x, and the the probability of success equal lambda over n. So lambda divide small n to the x power, and the probability of the failure is 1 minus lambda over small n to the small n minus x power. Okay, so the PMF of x equal k is like this. Okay, and this combination term can be expressed as n factorial over k factorial multiply n minus k factorial. Okay, so the PMF of the binomial when x equal k is factorial okay, and this expression can be expanded as follow. This term is 1 minus n multiply n minus lambda over n to the minus k power. Okay, and also this term is lambda to the k power over n to the k power. So you can write as the minus and the lambda the k power like this, and multiply, and this term, and multiply this term, and this term is the multiply this term and this term like this. Okay, so and the number of binary trial, that means small n as in goes to infinite, then according to the previous the three facts, you can find that this term goes to 1, and this term goes the earlier constant to the minus the lambda power, and this term, it goes to 1. Okay, so the PMF value goes factorial a minus lambda, like this. Okay, so you can get the following: the Poisson distribution PMF value when x equal k. Okay, and the x follow Poisson lambda. Okay, so to sum up, the x, to follow binomial small n, comma lambda over small n, then the PMF of x equal k equal another n factorial, and choose k like this, and like this, and so by using the expanded of the expression, multiply so as the n goes infinite, this term is 1. Okay, and this term is Euler constant minus 2, 2, the minus lambda power, and this term 1 minus the lambda over n converts to 0, and the k means the constant, so equal 1 minus k equal 1. So this term also goes to 1. So we can get their PMF. Okay. When x follow Poisson lambda. Okay. It is the key point and goes infinite. As we saw earlier, the Poisson distribution can be defined as the limit binomial distribution. Okay, that is the random variable x follow a binomial distribution with n binomial trials, and the probability of success is p, At this time, when the number of Bernoulli trial small n has a large value, enough large value, and the probability p has a very small value, and the n multiply p, which is the expected value of the binomial, and converts to ascertain their constant lambda. Okay, so and then the x of distribution approximately follow the Poisson distribution with the parameter lambda. Okay, for example, in this figure, blank line, this blank line is a graph of the Poisson distribution with lambda 5. So it is like this, like this. And the red color line is the binomial distribution with n equal 10, p equals 0.5. You can find that the mean, that is n multiply p equal 5. It is equal to the parameter lambda 5. Okay, and so the red line graph is like this, there is a difference from this Poisson distribution. Okay, like this. And then let's look at the binomial distribution of the green graph. With the n equal 50 and p equal 0.1. The expected value equal 5, also 5. In this figure, the green line graph is like this. Like this. Okay. So, as n, the Bernoulli trial n increase and the p decrease, then red line. So the green line graph is approximately this Poisson distribution. Okay, like this. And the blue line graph means a binomial distribution with n equal 1000 and p equal 0.005. So the mean has also five, and the blue line is like this. Okay, so blue line like this. Like this. So you can observe that it is almost similar to this Poisson distribution. Okay. And then let's compare the PMF values in the previous figure. Okay. So we assume that the random variable y follow the Poisson distribution with lambda equal 5. That is a black graph, and x1 follow the binomial distribution it is the the red line. Okay, x2 to follow like this, it is the green line. And x3 follow the binomial with n equal 1000 and p equals 0.005. This graph, the color is the blue line. So the probability of y equal 2 can be calculated as by using Poisson PMF like this. You know, the PMF of y equal to Mr. K equal Mr. K factorial lambda. Okay, so lambda equal 5. Okay, and k equal 2, then the PMF is so the value is the 0.08422. The first, the PMF of x1 equal to like this. So the value is 0.0439. This difference from the Poisson PMF value (0.08422 minus 0.0432). This value is the Poisson. This value is x1. So the difference value is 0.04032. And the PMF value of x2 equal to is 0.0779. So the difference equal 0.0 minus 0.0779 equal 0.00632. Okay, and as you can see, the PMF of x3 equal to is 0.08393. So the difference equal 0.00029. Okay, so you can observe that the difference with Poisson distribution is very small. Okay, so in conclusion, we can see that if n equal 1000 is large enough and p equal 0.005 small enough, so it approximates the Poisson distribution with its mean the n multiply p equal 5 as lambda. Okay.